Okay, so we'll start this lesson looking at the Galton board again, and we'll just experiment around with a couple of bits and pieces. So let's play it with a size 6 and a 50-50 and just recall what happens. So we get this particular shape going here. It looks a bit unusual. Oh, there we go. We got one on the right-hand side, etc., etc. Now what I can do is actually, if I pause this, I can change the left and right probability. So what I can do is actually change it to say 30-70. What that's going to do is favour one side. And if you can guess what's going to happen, what we'll do is the balls will sort of lean towards this right-hand side here, and the probabilities on the right will actually fill up a little bit more. So let's restart it and just see what happens. So notice how it becomes a little bit sort of favouring this side here, and it still produces the same general shape, but what it's going to do is just spread out a little bit more to the right-hand side. Okay, now if I change that to favour the other side, let's favour it considerably. Again, we get the build up over here. Okay, one ball still made it all the way down there, even if it's quite amazing actually. So there you go. And we can see this on a larger scale. Let's increase that to 15. And what I'm going to do is favour 100% right. So if I restart this, let's jump the speed up. Of course that's going to happen. So let's start to change that. Okay, and again, what I can do is just change these to get the balls to go in a certain way. Okay, but the amazing thing is, even if I do change it, it'll still form the same overall shape. It'll just be moved either left or right from the middle. Okay, so you see how when I've got a 64-36, okay, we still get this curve down here. So let's have a look at the notes now. So the effect of increasing P can be seen in the series of graphs below. So notice that if P in this case is 0.2, right, what we're going to get is a situation where the graph leans more to this left-hand side or the positive skew. Okay, if P is 0.5, we get it centered around that middle value. Okay, so the expected value for this would be 0.5 times 8. It'll be 4 if we do 8 trials. And if we have that P value higher, 0.8, it's going to be skewed to the left or negatively skewed. Right, and so this part of the course here, or the concept, can be demonstrated with a Galton board. We simulated tilting left or right to cause that skew. Right, so if we keep the probability fixed but vary n, what we get to have happen is if we have n being relatively low, i.e. around about 5, we get this sort of pattern here. At 15, we start to get that sort of curved pattern, and at 25, we do get that kind of nice looking, what we're going to call the normal distribution curve. And so if you think about it in terms of the Galton board, as you increase n, there are more options as to where the ball can finish, okay, thus spreading the possible endpoints of the balls. So as this n value increases, it just gives us more and more options. With relatively few options, the different ways to spread the ball is fairly low, but it just becomes more and more spread out. And that's just a summary of what we've just gone through with the Galton board there. Right, so let's try this out on a VCAR question. A biased coin is tossed 3 times. So whenever I see a coin, I think binomial, because a coin toss is either heads or tails. The probability of a head from the toss of this coin is P. That is, the chance of getting heads is P, and 1 take P is obviously not heads or tails. Okay, so again, we can see that this is binomial because it's either success or fail, and each coin toss is independent of the last. So in terms of P, the probability of obtaining 3 heads from 3 tosses. So 3 heads from 3 tosses is heads followed by heads followed by heads, which is p times p times p, which is p to the power of 3. What about 2 heads and a tail from 3 tosses? So you could go ahead and manually count all the different options of 2 heads and 1 tail, of which there will be 3, or we can use the formula, which is 3 choose 2. So from 3 choose 2 successes multiplied by the probability of success, which is p, and that will be 2 heads, so p to the 2, followed by 1 take p to the power of 3 take 2, which is 1, which is 3p squared, 1 take p. Right, if the probability of obtaining 3 heads equals the probability of obtaining 2 heads, and a tail, find p. Right, so they just want us to equate both of the previous. So we've got p to the 3 equals 3p squared, 1 take p. All right, so what we need to do is solve this. So it's looking like it'll be some sort of null factor law type problem. 3p squared, take away 3p to the 3, that's 4p to the 3, take 3p squared, equals 0. Let's factorize this thing. So we've got p squared 4p take 3 equals 0. P is equal to 0. P is equal to 3 on 4. Now, many of you will then rule out P is equal to 0 because you can't have a probability of 0. Yeah, you can. Okay, it seems pretty silly, but the Galton board for that would look as follows. That's a probability of one side equaling 0, which seems silly, but it's possible, right? So the value of P, the probability, has to be between 0 and 1, but can be inclusive of 0 and 1 themselves. So if you have a look at the report on the previous question, most students in the state got that first one right. Geez, wouldn't you kick yourself over that mistake there? Okay, so many students did P times P times P is 3P. Okay, you understood it, couldn't do the algebra. All right, so this one here, most students neglected the 3 for the possible arrangement. So 3 choose 2 gave us the 3 lots of head, and tail, or the variations of that particular configuration. All right, this one here, the cancelling out of P was rarely supported. So if you cancel P by dividing through by P in this case here, you assume that P can't be equal to 0, and for a probability P can be equal to 0. So bad assumption. So many students incorrectly assume that P could not be 0, which it can. All right, so where you can, girls, use the null factor law to get the solutions out. All right, Steve, Katerina, and Jess are 3 students who have agreed to take part in a psych experiment. Each student is to answer several sets of multiple choice questions. Each set has the same number of questions, n, where n is a number greater than 20. For each question, there are 4 possible options, A, B, C, or D, of which one is correct. All right, so again, this is reeking of binomial because you've got correct or not correct. Okay, and we're going to do this greater than or equal to, or greater than 20 times. All right, for each question, there are 4 options. 1 is correct. Steve decides to guess the answer to every question so that for each question, he chooses A, B, C, or D at random. Let X be the random variable, the number of questions that Steve answers correctly for a particular set. What's the prob that Steve will answer the first 3 questions of this set correctly? So correct, there's a 1 in 4 chance. Incorrect, there's a 3 in 4 chance. So first 3 questions in the set correctly is simply 1 over 4 multiplied by itself 3 times, which is 1 over 64. All right, so that's just correct, correct, correct. Find to 4 decimal places the prob that Steve will answer at least 10 of the first 20 questions correctly. So that is the probability that the random variable is at least 10. So that's going to be between 10 and 20 inclusive equals. All right, now it's important here to note that this will be usually a 2-mark question. And you're going to get 1 mark for the probability. All right, so I'm going to show you the probability first of all, and then I'll show you what you need to do for your 2nd mark, or in this case, what you should have done before you get your 2nd mark. So we're going to do our distributions, discrete, and what we want is CDF, okay, because that allows us to set a lower and an upper. We're going to do this 20 times, and the probability for success is equal to 1 in 4. Okay, and note that it said the answer is to 4 decimal places, so we are permitted to use the calculator on this one. We don't need to give an exact value. They're at 139. All right, now how do you get your 2 marks? Well, the other thing you need to do is indicate that this is binomial by writing that statement. So x is binomial. We're going to do it 20 times, and the chance of success is 1/4. So by identifying the distribution with the parameters, we get 1 mark, and our other mark comes from this number here. So you didn't have to write this statement here, it just comes from writing this number. Let's see what the report says. 1/64. Some students gave the answer only, where it was worth 2 marks. For questions worth more than 1 mark, working must be shown. Identifying the distribution with correct parameters was sufficient. Okay, so distribution there identified, 1 mark, and 1 mark for the evaluation of the probability. All right, expected value. So if you toss a coin 10 times, how many tails would you expect to get? All right, I hope you sort of say that on the law of averages, I would get 5. Now, we might have an unusual situation where I toss a coin 10 times and I get 10 tails, or I get 0. But if I asked you to bet, if I gave you each $100 and said, what would you bet will happen? I hope that most of you, or not most of you, all of you would say that the answer is 5. All right, so we call this in probability terms the expected value. Okay, so that we might get 0 to 10. The long-term average or expectation would be 5 tails. Now, in previous years, we would have used the expectation formula, or I would have used this using the expectation formula. And that is this formula here, but we don't need this year, okay? So in general, the expected value for binomial random variables, which is the only one we're doing in 2020, is equal to the number of trials multiplied by the probability of success. So here in summary is what it is. This is what we call the expected value. So E at capital X is equal to N times P, number of trials multiplied by the probability, okay? So if I have the probability of success of 0.3 and I do it 10 times, then I expect 3 to be my value. All right. Now, there's this other thing. So some notation as well. So our expected value, girls, is often denoted with this Greek letter called mu. Okay, so mu is equal to the expected value, which can be found by doing N times P. This thing here is called the variance, okay? And for the moment, I'm going to just say to you guys, this is very rare that I say this, and it grates on me to say it, but it is, use the formula. So when we want to calculate the variance, we're going to say that it's actually derived by doing N times P multiplied by 1 take P. And that's going to give us this thing called sigma squared, which is equal to the variance. Now, one more measure is sigma, which is equal to the square root of the variance, which is actually the standard deviation. What's the notation for standard deviation? We're just going to say that that's SDX, standard deviation of the random variable. So that one there, standard deviation, just is a measure of spread around the mean. And we're going to cover this a little bit later on when we talk about normal distributions, because it's going to make a little bit more sense. But again, All it is a measure of spread from the mean. All right, use the fact that the variance of x, so this is from the 2012 exam 2 question 3 continued. Use the fact that the variance of x is equal to 75 on 16 to show that the value of n is 25. All right, so the variance, we're going to use this formula here, which is np 1 take p. So var x is equal to np 1 take p. All right, and the variance is equal to 75 on 16. Now, P was the probability of success, and that was a multiple choice question, so it was 1 in 4. And we did it 20 times. No, we didn't do it 20 times. We don't know what n is. N times 1 over 4 times 3 over 4. 75 on 16 equals 3n on 16. Those will cancel out, and we'll do n is equal to 75 on 3, n is equal to 25 as required. So what does the examiner say? The question was answered quite well. Some students used the standard deviation, which was not necessary. Others did not know the formula for variance. Okay, so you needed to know and be comfortable with the use of that formula there. Again, it's a bit of a stretch at the moment, girls, because you don't know what the variance really gives us, but we'll just do a formula-based version of chapter 14 for the moment and get into it later. The probability of contracting influenza this winter is known to be 0.2. So either you get influenza or you don't get influenza. 0.2, 0.8. Of the 100 employees at a certain business, how many would the owner expect to get influenza? So that's the expected value. That's mu equals n times p. So we've got 100 employees, and the probability that they'll get the flu is 0.2. The expected value is equal to 20. All right, so now what we want to do is calculate this thing called the mean plus or minus 2 standard deviations. So let's get the variance, which is sigma squared. Now that's np 1 take p. All right, so I'm again just using the formulas. I know I'm a little bit more comfortable using them than you guys, which is np 1 take p. So we've got 100 times p, which is 0.2, times 0.8. So we'll chuck that into our calculator and say that that's 100 multiplied by 0.2 multiplied by 0.8, which is 16. So our variance, that's what our variance is, 16. Now our standard deviation is going to be the square root of the variance. So that is, in this case, going to be sigma, which is equal to 4. So our standard deviation, in this case, is equal to 4. So what they want us to do is work out what the mean plus 2 standard deviations is. All right, so the mean plus 2 standard deviations, so let's go and work out the interval. So the mean is here, there's 1 standard deviation is 4, so it's going to be 20 take away 2 times 4 is 2 standard deviations to the left. That's 20 plus 2 times 4 is 2 standard deviations to the right. That's going to be 12 to 28. All right, and what that actually means, and I'll go on to explain this a little bit later because we interpret these intervals, is that 95% or between, actually not or, 95%, what are we trying to say here? We can be 95%, no, right, we can be 95% sure or prob of 0.95 that the number of employees to get flu with just a U will be between 12 to 28. Right, so that's what that statistic means, but again, we'll cover more of that later. What I'm really happy if you're able to do is just to use the formulas to get these values just for the moment. All right, the probability of winning a prize in a game of chance is 0.45. No, we're not going to do this question. We'll save this for later. Okay, so just a couple of key things to finish up with on discrete probability. Be careful which x values you enter for the upper and the lower. The values you choose are always included in the probs. So in this case here, if you want between 1 and 4 inclusive, the lower value is 1, the upper is 2. If you want more than 1 and less than and equal to 4, then that is the statement that you're looking for, that one there, which means you need to put between 2 and 4, okay? So remember that this is discrete probability. Greater than 1 means 2 or more, okay? This one here means it's going to be 2 and 3 that you actually put in. Right, there's your questions there, girls. Okay, so it's not many, but it's a bit of practice using their skills. And this problem here, we'll save this till next lesson.